Let's do another thought question. With the trajectory for an elongated object like a rectangle, would it be changed if the object were rotating? So let's think about this same rectangle that we've been thinking about. If you throw it in the air, and you can do the experiment for yourself and give it a little rotation as you throw it in the air, you find again that the center of mass, represented by these red dots, would actually follow the same trajectory. Now, if instead we labeled one of the ends with these green dots, you can see that, yes, that the green dots, which would mark one side of it, will change the trajectory from the traditional parabola. But what's really happening is that if we put the centers of masses right on top of each other, the center of mass, which is following these red dot trajectories, and the green are just rotating around them. So the center of mass is doing its own thing, and the rotation around that center of mass, which is represented by the green dots, is actually decoupled from the trajectory of the center of mass. We can talk a little bit more about rigid body rotations, the kinematics of them. We can describe these rotations with parallel concepts to what we saw in linear motion. So for instance, in linear motion we had distance in x, y, or z. For rotation, we can talk about the angle of rotation, and we typically use the unit of radian instead of degrees for these measurements and for this discussion. That makes it easy because 180 degrees is equal to a rotation of pi, 360 is equal to a rotation of 2 pi, and we get a directly proportional relationship between the distance that's traveled by the end proportional to the angle in radians, which you don't get when you use degrees. So when you're doing these questions, make sure that you're always using radians and not using degrees, and if you have degrees, make sure you convert. For velocity, which in the linear case we have meters per second, instead we now have an angular velocity, which is radians per second. Omega is the term that we use for that. It's denoted as the change in angle over the change in time. And for acceleration, again, we have an angular acceleration. Again, this is the change in angular velocity with respect to time, and the units are radians per second squared. The units for angular velocity are just radians per second. So this all follows directly from what we did for linear, and if we had time, we would develop all the equivalent equations of motion as we did for the linear motion. Because we've already developed them for linear motion, you can just use them directly, and we'll do one example today where we use them. So let's talk a little bit about this. Let's say we have an extended object. In this case, it's a triangle. How do we talk about its angle in radians? Well, what we need to do is come up with some fiducial, and so we'll use the green dot that's located in this lower left corner of the triangle. And again, remember, we're going to use our angle in radians, so we need to convert from degrees to radians by multiplying by pi over 180, or you can also multiply by 2 pi over 360, which is equivalent. So let's say if at time equals 0, the rectangle looks like this. In order to figure out what the angle for that green fiducial marker is, we need to figure out where it's located with respect to the x and y axes. In this case, the angle is 220 degrees. If we take the same object and we now rotate it, and it rotates 1 second later by some amount, we can measure the new angle. In this case, it's 280 degrees. Again, we can use degrees as long as we make sure we convert to radians. If you multiply 220 times pi and divide by 180, you get 3.84 radians, and for 280 you get 4.89 radians. We can calculate the velocity, so let's assume that this change in the angle has occurred over the 1 second, as explained, and it was moving with a constant velocity. If we do that, then we can find that the change in theta as a function of the change in time is 4.89 radians minus 3.84 radians, that's the numerator, and we divide it by 1 second. So we get 1.05 radians for 1 second, or 1.05 radians per second. Same thing with the acceleration. Let's assume now that this motion of rotation has occurred not with a constant velocity, but with a constant acceleration. So, and that there was an initial velocity of 0 radians per second. and an acceleration of 1 radian per second squared. So now the question that we can answer is, what is the final angular velocity at 1 second? Again, the change in the angle is the same, 1.05 radians, and the amount of time that's elapsed is the same, 1 second, but instead we want to use our kinematic equation. Remember, the linear equation is vf squared equals v naught squared plus 2a delta x, and so we can relate this to now our omegas, alphas, and change in thetas to be very similar. Using these equations, it's very straightforward to solve for omega f, and we get 1.45 radians per second will be the velocity at 1 second.